I'm going to talk about a paper on the power of multiple anonymous messages. This is joint work with Badih Ghazi, Ravi Kumar, Rasmus Pagh, and Ameya Velingker. And I'm Noah Golowich. I'll begin by reviewing the central and local models of differential privacy, and then I'll discuss the shuffled model of differential privacy, which is the main topic of this talk. And then I'll talk about our two main results in our paper. The first is a lower bound for the frequency estimation problem in the single message shuffle model. And roughly speaking, what we show is that the phenomenon of privacy amplification by shuffling leads to optimal protocols for the frequency estimation problem. Then I'll talk about how we can in fact surpass these lower bounds using the multi-message shuffle model. And I'll talk about how we can make those protocols communication efficient. We're going to assume there's a universe U, which is simply a finite set, and there's n users, each of whom holds an element of U as their data point. The collection of these n users' data elements is called their data set, which is denoted by capital X. The goal in differential privacy is for the users to release certain statistics of the data set X in a way that respects each user's individual privacy. In the central model, the way they do this is they each send their data point xi to a trusted analyzer, which may be, for instance, a government, which then adds noise to the desired statistics of the data set. And we denote the output of the trusted analyzer by A of X, which is a random variable. The algorithm A is then defined to be epsilon delta differentially private. If, roughly speaking, for all neighboring data sets X and X prime, which differ in a single element, the distribution of A of X is similar to the distribution of A of X prime. Formally, we require that for all events T, the probability that T occurs under A of X is similar to the probability that T occurs under A of X prime. Now, one issue with the central model of differential privacy is that a trusted analyzer may not be available in many applications, and this motivates the local model of differential privacy. So here the analyzer is now untrusted, and therefore the users must add the privacy-preserving noise themselves. So in the local model, in addition to an analyzer A, there's a local randomizer denoted by R, and given an input xi, the user sends R of xi to the untrusted analyzer, which then performs an analysis on the R of x1 to R of xn. And the algorithm induced by the local randomizer R is defined to be epsilon delta differentially private in the local model if the function that takes x to R of x is itself epsilon delta differentially private. So here we view R as a function on data sets of a single element. And in particular, what this requires is that the distribution of R of x is similar to the distribution of R of x prime for any x and x prime in the universe. And this necessitates adding a lot of noise. And in particular, for simple problems, such as the problem of aggregation, the error for local model of differential privacy has to be on the order of the square root of the number of users. This is often very undesirable in practice. And in this talk, I'll discuss one solution to this problem, which is the shuffled model of differential privacy. So here we assume that there's a trusted shuffler, denoted by S, between the users and the untrusted analyzer. And given the user's inputs R of x1 to R of xn, the trusted shuffler randomly permutes them and sends the permuted messages to the untrusted analyzer, which then outputs A of the shuffled messages. Now here's how privacy is defined. The algorithm induced by the local randomizer R and the shuffler S is epsilon delta differentially private in the shuffled model if the function which takes the data set x1 to xn to the shuffled output of the concatenation of R of x1 all the way up to R of xn is itself epsilon delta differentially private. One important distinction I'll make in the shuffled model is that of the single message versus the multi-message shuffle model. In general, R of xi may output m distinct messages, in which case the shuffler S applies a random permutation to m times n messages. In the special case where m equals 1, we're going to call this the single message shuffle model, and here the shuffler only permutes n messages. In the general case where m is bigger than 1, we will call that the multi-message shuffle model. So one reason to care about the single message shuffle model is a phenomenon that was observed in some recent papers called privacy amplification by shuffling. And what these recent papers showed is the following. If we have a local randomizer R which is epsilon L 0 differentially private in the local model for some epsilon L bigger than 0. Then when we shuffle these messages, the resulting single message shuffle model, denoted by SR, is epsilon S delta differentially private in the single message shuffle model for some privacy parameter epsilon S, which is a lot less than epsilon L, and for some delta which is not too large. These results are neat because they can essentially allow us to design single message shuffle model protocols in a black box manner by first taking a locally differentially private protocol with a bad privacy parameter, then amplifying it using privacy amplification by shuffling. And one application of this design principle is for frequency estimation protocols. So here, the universe is the set of integers from 1 to b, and the goal is to compute the frequency of each element j from 1 to b, namely the number of users I, such that xi is equal to j. And we measure the error for frequency estimation by additive error. So it's the maximum over all j of the true frequency of j minus the estimated frequency of j by the algorithm, and we take the absolute value of that. So this is an integer between 1 and n. Now, using amplification by shuffling, it's possible to show the following upper bound on the error of frequency estimation in the single message shuffling model. You can show that you can perform frequency estimation on a domain of size 1 to b with error which is roughly the minimum of n to the 1/4 and b to the 1/2 up to polylog factors. To get the upper bound of roughly n to the 1/4, you shuffle the output of the local randomizer given by rapport. And to get the upper bound of b to the 1/2, you shuffle the output of the local randomizer given by Warner's randomized response. And our first main theorem is that this upper bound is actually optimal for all single message shuffle model protocols. In particular, what we show is that any differentially private single message shuffle model protocol for frequency estimation has additive error, which is the minimum of these two quantities, namely n to the 1/4 and b to the 1/2. Okay, so now we'll discuss the proof of this theorem. The first idea of the proof is to use a reduction that was observed by Chu et al. A few years ago, which shows that any epsilon S delta differentially private protocol in the single message shuffle model implies the existence of a equivalent protocol in the local model, which is epsilon S plus the natural log of n delta differentially private. And what this means is that if we can show a lower bound for locally differentially private protocols frequency estimation, where the epsilon parameter is roughly the natural log of n, we can get a corresponding lower bound for the single message shuffle model. And this is exactly what we do. So we show that if the local model privacy parameter epsilon L is roughly equal to natural log of n times a constant factor, and delta L is sufficiently small, then any epsilon L delta L locally differentially private frequency estimation protocol must have error at least 1 over root n times e to the epsilon L over 4. In addition to implying the lower bound on shuffle model protocols, this theorem also improves upon previous work by Ducci et al. For locally DP frequency estimation. They showed a lower bound of 1 over root n times e to the epsilon L. So our lower bound improves on the prior work in the dependence of epsilon L in the denominator, which is a polynomial factor in n when epsilon L is a constant times natural log of n. And I also note that the lower bound by Ducci et al. Only applies to the case of pure differential privacy, namely that where delta L is equal to 0, whereas our theorem applies in the case of proximate DP, where delta L is small but positive. Okay, now here's the proof idea of the lower bound for local differential privacy. Roughly speaking, we want to use Finow's method. And what this means is that letting alpha be the desired lower bound on the additive error, the goal is to show a certain upper bound on the mutual information between two quantities. To define these quantities, let V be a uniformly random element of the universe, and let X be a perturbed version of V. In particular, X is equal to V with probability alpha, and it's a fresh draw from the universe with probability 1 minus alpha. And the main step in our lower bound is to show an upper bound on the mutual information between V and R of X of roughly alpha to the 4 times n times e to the epsilon L. Now, what makes this proof a little bit tricky is that this upper bound is actually false for general randomizers R, even those which satisfy epsilon L delta differential privacy. In order to show this upper bound, we additionally have to use the fact that R can be used together with an analyzer that leads to a protocol with error bounded above by alpha. Okay, so the takeaway from our lower bounds for the single message shuffle model is that we must have error which is polynomial in either n or b. Now this could be quite undesirable in practice and make the resulting statistics unusable. And next we'll talk about how to get error which is polylogarithmic in n and b using the multi-message shuffle model. Before doing so, I'll first review the measures of efficiency that will require our protocols to satisfy. The first is communication complexity, and that's very straightforward. It's just the total length of all m messages output by a single user, which is measured in, say, the number of bits. To define the computational complexity of our algorithms, we're going to only focus on the computational complexity of the analyzer, because the user's algorithms are always going to be very efficient. And an issue here is that the domain size B might be much larger than the number of users n, so it could be infeasible to compute the frequencies of all elements j in the domain from 1 to b. The solution is to require the analyzer to output a frequency oracle FO, which takes as input a query j from 1 to b, and outputs a frequency fj, which is the integer from 0 to n, denoting the estimated frequency of item j in the data set. And we measure computation by measuring the query time, which is the time taken by a single query FO of j. And one more resource we'll allow our algorithms to use is that of public coins. So up to now, all protocols I was talking about had private coins, where the analyzer used their own local randomness to output the randomized response R of xi. For one of our protocols, we will additionally allow all the local randomizers to access a common random string of public random bits. And these bits can also be viewed by the untrusted analyzer. Okay, so here's our main theorem for efficient frequency estimation in the multi-message shuffle model. We show that there exist protocols which are epsilon delta differentially private and have the following properties. There's two protocols in particular that we introduce. The first is based on the Kaupman sketch, and the second is based on Hadamard response. Both of these protocols achieve additive error, which is polylogarithmic in B, and communication, which is polylogarithmic in N and B. But they differ in the query time. The Kaupman sketch uses public coins and has query time, which is polylogarithmic in N and B. The Hadamard response does not use public coins, but it has query time, which is linear in the number of users. And roughly speaking, the public coins in the Kaupman sketch are used to perform hashing, whereas the Hadamard response achieves a similar functionality in a different way. Okay, now here's the idea for the two multi-message protocols. The first step is to view frequency estimation as B parallel aggregation problems. In the jth problem for each element j, we simply want to add up the number of users holding holding the item j, which is going to be a bit, either 0 or 1 for each user. And it was observed by Chud in 2018 that there's a local randomizer, which we denote by RAG, that can perform aggregation with polylogarithmic error in the shuffle model. Now, by concatenating B of these local randomizers, one for each of the domain elements, we can get a shuffled model protocol with B types of messages, and where each user outputs B messages that can estimate the frequency of each item j. The issue here is the communication has to be at least on the order of B, and this might be very, very large and make it infeasible in practice. So the second idea of our proof is to use a trick, either from Kaupman sketch or Hadamard response, to avoid having to send B separate messages. And for the rest of this talk, I'll focus on our protocol based on the Hadamard response. You can see our paper for the protocol based on the Kaupman sketch. So I'll begin by introducing the Hadamard response, which is actually a locally differentially private protocol for frequency estimation. For simplicity, let's assume that the domain size B is 1 less than a power of 2. So we can consider the Hadamard matrix, which has B plus 1 rows and columns, and delete the first row. And we're going to denote that resulting matrix H. Each of the b times b plus 1 elements of H is either a -1 or a 1. And here's how Hadamard response is defined. For an element x from 1 to b, R of x, which is going to be an integer from 1 to b plus 1, is distributed as follows. With probability e to the epsilon over 1 plus e to the epsilon, R of x is chosen uniformly from the columns k of the matrix H, such that hxk is equal to 1. And with probability 1 over e to the epsilon, R of x is chosen uniformly from the columns k of the matrix H, such that h of xk is equal to -1. And it's known that this protocol gets error roughly root n in the local model. Our main goal here is to modify this protocol in a way that it remains communication efficient, but it gets error that's only polylogarithmic in n and b in the shuffled model. So here's how we do this. Given an input x in the domain b, the local randomizer is going to output several messages. One of these messages can be interpreted as a signal message, which gives information about what x is. We denote this message by m, and it's simply a concatenation of log n indices of the columns of the Hadamard matrix H, m1 through m log n. And each of these items is uniform over the columns of H, such that h of xk is equal to 1. These are the columns that were outputted with higher probability under Hadamard response. Additionally, we're going to output a bunch of noise messages. In particular, let rho equal an integer on the order of log 1 over delta over epsilon squared. And we denote these noise messages by m tilde 1 through m tilde rho. And each of them is simply drawn uniformly from the log n tuples of integers from 1 to b plus 1. Each of these elements is completely independent of x, and they're added purely to preserve differential privacy. So the local randomizer R of x is simply the concatenation of m with m tilde 1 through m tilde rho. And roughly speaking, we have privacy because we've concatenated enough messages, enough indices of columns of H in that single signal message in order for the analyzer to determine estimates for frequencies for each element in the domain. Privacy is a little trickier to show, but roughly speaking, it follows because the number of noise messages, m tilde L, that are consistent with any given row of the Hadamard matrix is a binomial random variable, which is sufficiently smooth. And by consistent with the row X, what I mean is that those messages are messages that the user could have outputted if their true index, if their true data point was X. So we have several additional results in our paper. First is we show a lower bound in the sample complexity of the selection problem in the single message shuffle model. For the selection problem of D elements, we show a lower bound of omega D, and this is tight up to a log factor because it's known that you can solve this problem with O of D log D samples. We also show a corollary of the Hadamard response-based protocol that I talked about, which shows how to efficiently implement certain families of non-adaptive SQ algorithms in the shuffle model. In particular, we show this for SQ algorithms which are sparse, in the sense that for any element of the universe, there's a bounded number of statistical queries for which that evaluate to 1 on that element. Finally, we have applications of upper bounds of frequency estimation to problems such as range queries and quantile estimation. And you can find our paper at this link. I'll conclude by discussing some open problems. One open problem is whether or not it's possible to decrease the roughly linear query time that's achieved by Hadamard response for private coin frequency estimation. We know that if we allow public coins, the Countman sketch will decrease this query time to tilde of 1, but we don't know whether or not this is possible with only private coins. Another major open problem is determining the sample complexity of the selection problem on D elements in the multi-message shuffle model. Chodal observed that there's a protocol which achieves sample complexity O of root D, which is smaller than our lower bound for the single message shuffle model by a quadratic factor. But in the central model, you can get O of log D sample complexity, and it's unknown whether or not you can do this well in the shuffle model. So thank you for listening.